Hi, we have one more thing to learn in order to solve quadratic equations, and that's something you might have seen before called the quadratic formula. Before we get there, I wanted to go over some of the do's and don'ts for working with solving quadratics before we get to the quadratic formula. So, in this case, we first see the equation. It's quadratic equals 0, which is always good. I make a quick mental sketch. My sketch should show a parabola that goes to the origin. It's because the y-intercept is 0. And should go down initially, so down initially because of the negative 12, but up eventually because of the positive 3x squared. It's going to turn it back around. For the factoring, it's just a matter of looking at common factors. 3x squared and 12x have a common factor of 3x. So I take out a 3x, show it a good time, and then I have x minus 4. Those are the two factors, and this is exactly where I use the zero product rule. 3x times x minus 4 equals 0 means either 3x equals 0 or 4x minus 4 equals 0. So x equals 0, x equals 4. So that's the correct way to solve this using the most efficient and appropriate methods available. Now, this next approach is the same equation, and I want to show you what I've seen people do before. They add the 0 term, then they take the middle term b, they xbox it, end up with 0 and 12 numbers that multiply to get you 0 and add up to negative 12. Then they factor by grouping. You've got the first two and you got the last two. And then they take out a common factor of 3x squared in the first set. Now I'm going to stop right there. This is exactly what you needed to do to solve this equation in the first place. So you just did all of this extra legwork for absolutely zero reason. Nonetheless, people will still factor out a 0 inexplicably, I don't know how, and then get an x minus 4, because 0 times x minus, I don't know. This is all make-believe math, but I've seen people do this before. Other people will factor out a 0 and leave it as 1x minus, well, I don't know what they put, but it's not right. So anyway, common factor is x minus 4, if you're still doing this make-believe, and then you get the two factors, but anyway, that gives me the two solutions, but I should have gotten there a lot quicker with a lot less pain and suffering. So this is good. This is not so good. It's not that it's wrong, it's just wrong. Alright, 3x squared minus 12. Notice how different this is. It's just like the other one, except it's not minus 12x, it's minus 12. That changes the mental sketch because this is just the parabola 3x squared that shifted down 12. So the vertex will be on the y-axis. This time, I look for common factors, but there's only a factor of 3, leaving me with x squared minus 4 equals 0. This I recognize as a difference of squares. X minus 2 times x plus 2 multiplies to give me x squared minus 4. Then I could zero product rule this mofo, and I get x equals 2 or x equals negative 2. Or, you want to be super smart, you could also add the 12 to both sides, then divide both sides by 3, and then take the square root of both sides. You can do this if you remember the absolute value, and then to get rid of the absolute value, you have plus or minus 2. So this is good. Either of these is good. I totally condone both of them. Here's what I see some people do. They'll take 3x squared plus 0x minus 12, and then they'll xbox with the 0 on the bottom, and they end up with the two factors. They factor by grouping. Look, this isn't wrong. You get the right answers. It's just craziness. Why would you do all of that work if you didn't have to? So the important thing here is if you have a two-termed expression, look for common factors. Sometimes you'll just have the common factor and then you can just go zero product rule. Other times you'll take out a common factor and then you'll see a difference of squares or something. So that's what you need to look for with two terms. Don't start using three-termed arithmetic in order to do your math for two terms. In other words, these are special cases. You should treat them special, and they're usually easier. So, next issue, we have 3x squared plus 12 equals 0. That's the same parabola, goes up this way. But if you notice the mental sketch, you'll recognize that there are no x-intercepts here. 3x squared plus 12 never equals 0. Should make sense. Positive number plus positive number won't ever equal 0. Anyway, I'm going to solve it anyway by using the same technique I had before. First, I factor out a 3. And then I divide both sides by 3, and I have x squared plus 4 equals 0. Now I'm going to subtract 4 from both sides. Even though I know there's no real solution, we're in Algebra 2 now, we can find more than just real solutions. We can find not real solutions. So I have x squared equals negative 4. That means absolute value of x equals 2i, because remember the I is the square root of negative 1. Then our solutions are plus or minus 2i. This is good. You could also subtract the 12, divide the 3, and then you're back where you were before with the square roots, and you still have plus or minus 2i. No problem. I got no problem at all. I do have a problem with adding an extra 0x and using a 3 form. Actually, here, somebody's actually completing the square, which is, again, very strange. Or, this is the worst one. There's no solution. Of course, there's a solution. It's just not a real number. We've expanded the number set. Now there's real numbers and there's not real numbers. Those are when you take the square root to -1. We call them complex or imaginary numbers. So whenever you see something that has no real solution, do not say that there is no solution. Rather, find the imaginary solution that goes with it. So, once again, no 3-term algebra when you have 2 terms, and don't say no solution anymore. There's always going to be a solution. It just might not be real. Here again, we've got the quick mental sketch issue. This is a situation where I recognize a perfect square trinomial because if I see x squared and 25, I know they're both perfect squares. 5x doubled is 10x, so this is a perfect square candidate. So I just jump straight to the factors, take the square root of both sides, and I get x equals 5. Graphing x minus 5 squared is a parabola that's shifted to the right 5 units, which makes sense. There's 2 of the same solution. The vertex is the x-intercept in this case. Here's stuff that's crazy. Don't recognize that this is a perfect square at the beginning. So that's fine. You put up an X box. That's fine. But once you recognize this is -5 and that's -5, you'd be like, oh, this is a perfect square. If these two numbers are the same, this is a perfect square. So you should stop with the long form and just cut to the chase. You have my permission to cut corners when there's something that's obvious, like a difference of squares available to you. So, it's not wrong. It's just a waste of time. 9x squared plus 30x plus 25. I'm going to do my perfect square check. We've got 5 times 3x is 15x. Double it, you get 30x. So this is a perfect square again. Nice and easy. And what I did do is the same thing I did in the last one. The wrong way to do this would be to use your trinomial factoring. The only reason it's wrong is because look at all these large numbers you got to work with. You have all this effort when you could have just recognized a perfect square to begin with. Not wrong, just kind of, x squared minus 8x plus 7. What's the deal here? Well, because the coefficient on x squared is 1, these two numbers in my x box become the constants in my factors. I do not have to do the long form factoring. I now have permission to cut to the chase. X box numbers go right into your factors only when the coefficient on x squared is positive 1. Very good. Not so good. Saying, all right, I'm going to use the long form factoring. Again, I condone this. This is a great method, but it's unnecessary when the coefficient on x squared is 1 because these two numbers show up here and here. You can skip the long form. Sorry, this will be over soon enough. Now right here, I have a quadratic expression that is unfactorable. So what am I going to do? The only way to solve unfactorable quadratics is to get this mofo into vertex form by completing the square. So I will complete the square. There's videos on this if you want to rewatch. As I complete the square, I send over the constant term, take the square root of both sides, and then I add the 7/2 to both sides, and I get my final solutions. So this is good. You can also remember, whenever you have answers that are not perfect squares, you give me an estimate, just a ballpark, so we can get approximations for the two values. And then, of course, we're going to check all these with Desmos. The worst thing you can do is to look at this and say it's not factorable. Once again, not only will all quadratics now officially always have solutions, they just might not be real. But even non-factorable quadratics are solvable. Just because you can't factor it doesn't mean you can't solve it. Of course you can solve it. It takes a little bit more work. So save your work for those kinds of situations. All right, so for here, the issue is what's the right way versus the wrong way? Right way is to recognize that it's factorable and to factor it. Now what I'm doing here on the right side is I'm completing the square. Nothing I do here is wrong. It just is highly probable that you're going to make some kind of careless error. So completing the square when a quadratic was factorable, it's kind of a math crime. It's like, why are you doing all this pain and suffering? If you would have just noticed it was factorable from the beginning, you wouldn't have had to do all of this work. And look, I got the same solutions. It just took me so much longer to get there. So think before you act. Last but not least, I have this equation, and this is what happens when a lot of times you end up with equations that are not immediately in the kind of form you see in textbooks. So what you need to do is you want recognize that there's an x squared, and when I FOIL, there will be another x squared. So you say this is a quadratic equation for show. Then all I have to do here is say, well, the quadratic sets equal to 0. That's how I solve. I have to start with the equal to 0 part. So in order to do that, I need to unleash these variables from their prison using the FOIL algorithm: x times x, negative 3 times x, negative 2 times x, and negative 3 times negative 2. And then we also have the extra add x. I collect like terms on the right-hand side. Now I have quadratic equals quadratic, not quadratic equals 0. So I'm going to subtract the x squared from both sides. I'm going to add 4x to both sides. That gives me a 0x. And I'm going to subtract 4 from both sides. That's when I recognize, oh, we got a difference of 2 squares here. I'm going to factor, use the zero product rule, and I'm good to go. Don't forget, when you're solving equations like this, you should definitely check your answers by hand. This is an opportunity to improve your arithmetic skills to make you a better mathematician in the future. So I'm going to skip this. This will be in the notes. You can follow along or pause the screen or whatever. The other thing is, don't forget to use your Desmos checks. Get absolute verification. And when you do your Desmos check, you're checking the given equation, not the factored form. So use this is the right-hand side, this is the left-hand side, and here's where they intersect, which is my two solutions. So thanks for watching. Have a great day.